everyone. Okay, let's start 10.4 energy and rotational motion. I have two very important quantities to introduce to you in this section, and then we'll do one example. So let's consider a rigid body that's rotating about an axis of rotation. I've drawn an example here. This is the rigid body, there's the axis of rotation. You can think about it as being separated into all of its individual mass elements. So each one is labeled from 1 to n. And for example, this piece here, mass 1, which is just a particle in that rigid body, it would have mass 1. It's at a distance of r1 from the axis of rotation, and it's moving with speed v1. So if we do this, we can write the total kinetic energy for that rigid body as the sum of the kinetic energy of all of these mass elements that make up the object. So let's do that. K is the sum over I of 1/2 mi vi squared. And that would give us the total kinetic energy for that object. That's the linear kinetic energy. So let's convert that into a rotational kinetic energy by changing these variables, linear variables, into the corresponding rotational variables. To do that, I'm going to plug in V equals R omega, the relationship from the previous section. So I have Vi for each element, Ri. Omega I haven't labeled because this object is rotating at one constant angular frequency, or at least at one moment in time, the entire object is rotating with the same angular frequency. So we don't need an I subscript there. Okay, so plugging that in here for V, we have K equals 1/2, the sum over I, mi Ri squared omega squared. I pulled out 1/2 since it's a constant. And then we can kind of group together this sum here, the sum over I, mi Ri squared, and then omega squared at the end since it's also a constant. I want to do this because this quantity in the brackets is an important quantity called the moment of inertia. So it's labeled capital I here. It's the sum of the mass of all different elements making up the object, and their distance Ri to the axis of rotation. It's Ri squared. So the total moment of inertia has units of kilograms meters squared. So this moment of inertia is a rotational mass equivalent. So it often takes the place where mass would with our linear quantities. And it is a measure of inertia. So an object with a higher moment of inertia would resist changes to its rotational motion. So it would be harder to push it and set it into rotation than it would for an object with a lower moment of inertia. The moment of inertia is not a constant for a specific object. It actually depends on the axis of rotation, right? Because R is involved in this expression here. So it is specific to the axis of rotation and then the mass distribution of the object. So generally objects will have a higher moment of inertia if there's more mass distributed further away from the axis of rotation. Okay, so let's replace that here by I, and now we have rotational kinetic energy, K equals 1/2 I, the moment of inertia, times omega squared, the angular velocity squared. And so the units here would still be joules for kinetic energy. We have kilograms meters squared for moment of inertia and radians per seconds, and then that squared with that angular velocity term there. Okay, let's look at how this applies to an example. A student participating in an engineering design contest designs a widget as shown in the diagram consisting of 3 masses joined together by lightweight connecting rods as shown. A, suppose the widget is rotating in the plane of the page at 9 radians per second about the 300-gram mass. What are I and K? B, suppose the widget is rotated about the line connecting the 150-gram and the 250-gram mass at the same angular speed. What are the new I and K? Okay, so for part A, it's rotating about this 300-gram mass. So you can imagine a pin in the board there, and then it will rotate around that point, and with a rate of 9 radians per second. So to calculate the moment of inertia, we can use the formula, the sum of mi squared for each of the masses. And r here is the distance to that 300-gram mass, since that's the axis of rotation. So we have 0.3 kilograms for this first part, which doesn't end up contributing since it's at 0, plus 0.25 times 0.08 meters squared, plus 0.15 kilograms times 0.06 meters squared. So these are just distances to that axis of rotation, or radial distances, we don't need any signs, they would be squared anyway. And also, you can just draw the straight line distance from that point, axis of rotation, to where the mass is, and that's the distance we're using. All right, so that gives 0.00214 kilograms meters squared. Then we can just plug it in to find the rotational kinetic energy, 1/2 I omega squared, so 1/2 0.0214 kilogram meter squared times 9 radians per second squared, which gives 0.0867 joules. All right, I'm just going to erase so that we can do part B. Okay, so for part B, the axis is now through the 250 gram and 150 gram masses here. It's in red, I don't know if it's really showing up there, but that's the axis. You can imagine it's rotating like that around that point. So both the 250 gram and the 150 gram masses are now at r equals 0, but we need to find r, the distance down this center of the triangle, to the 300 gram mass. There's more than one way to do this, but I'll use the large triangle and find theta here. So theta of this right angle triangle. Tan theta is 8/6 centimeters, which gives 53.1 degrees. And then we can use that angle here, the r and this 6, and do r equals 6 centimeters sine 53.1. Of course, you could have done the other triangle, but this gives 4.8 centimeters. And with that, the other two objects don't contribute to the moment of inertia here because they are at 0, so we just have mr squared for the 300 gram mass. So 0.3 kilograms times 0.048 meters squared, which gives 6.91 times 10 to the negative 4 kilograms meters squared. And then we can plug that in to find the rotational kinetic energy when it's rotating about this axis of rotation. So K is 1/2 I omega squared, 1/2 6.91 times 10 to the negative 4 kilograms meters squared times 9 radians per second squared, which leaves us with 0.028 joules. So you can see from this example that both the moment of inertia and the rotational kinetic energy do depend on the axis of rotation for any object or mass configuration.